Okay, hi everyone. Making sure everything is going well because I've got a lot to teach you in this lesson. This is section 8.5, which is graphing the solutions of these systems of differential equations. And it's a long section, lots of stuff going on in there, so I'm not going to try to do everything, but I'm going to hit the highlights and give you the forest, as it were, okay? And then you can obviously read through the book to get more of the details. So this is the one I begin with. Suppose we have this system of differential equations, which, just to remind you, you can write it like this. The vector x prime is equal to this matrix times x, or if you want to, you can be clear that this thing means x prime and y prime, where these are scalar valued functions. And then you still have this, and this becomes x and y, or you can write it out. X prime, of course, x prime means the derivative. The derivative of x is equal to, if you multiply this out, you're going to get negative 3x plus y. And then y prime, you multiply this out, you're going to get x minus 3y. So there's the system. So either any of those are fine. I'm going to be using all three of them as we go. So one way to do it is to do something similar to what we did when we did Euler's method of basically making kind of a slope field. So basically at every point in the whole plane, you determine which way is the solution going. What's the direction of the trajectory. And so just as an example, suppose we're at the point 4, 2. So here's the xy plane right here. Okay, and you're at the point 4, 2 right there. What direction is the water going? If you think of this as being kind of like water that's flowing over a surface, and at every point on the surface the water is flowing a certain direction. What direction is the water flowing right here at the point 4, 2? So what do? All you do is you stick 4 in for x and you stick 2 in for y, and you're going to get negative 12 plus 2 is going to be negative 10 in the x direction. And then 4 minus 3 times 2 is negative 6, and so it's going to be negative 2 in the y direction. So if you're right here, your movement is in the negative x direction, which of course is this way, and it's also in the negative y direction, which is this way. And the x direction is more pronounced, so you can think of it as being like a slope, which is going 10 in this direction for every 2 in the downward direction. So it's like a 5-to-1 ratio. So this movement here is such that this length here is 5 times as great as that length. So that would give you the direction of the flow at that particular point. And you could do that at every point in the whole plane. And then once you have that, then you could basically take a bubble or a little piece of styrofoam and set it there and let it follow the arrows and see once where it goes. Okay, so that's basically, as I understand it, what computers do when they calculate these things. Of course, they have no problem doing lots of calculations very quickly. So another way to do it is to actually get the solution, and we know how to get the solution from what we did in the last section. So we first of all need to find the eigenvalues, and so the way you find the eigenvalues is to subtract lambdas down the diagonal and then take the determinant of it. So when I subtract lambdas, it's going to be like this. And now, of course, the determinant is this times this minus this times this. Notice that you have a whole lot of negatives there, and so if I multiply all those negatives out, I can get rid of all of them. And so this becomes lambda plus 3 times lambda plus 3, subtract 1. So that's what I get. It's going to be lambda squared plus 6 lambda plus 9 minus 1 is 8, and then that factors into this. And you can see that the two eigenvalues are going to be negative 4 and negative 2. Agreed? So once you have the eigenvalue, how do you find the associated eigenvector? So you start with lambda is equal to negative 4, and basically kind of the shorthand way to do it is you just take this again and you let lambda be negative 4. Of course, if you subtract the negative 4, it's going to be adding 4. Subtract the negative 4, you're going to be adding 4 there. And so this is going to become a 1, 1, 1, 1 times xy is equal to 0, 0. And the reason why that is because you start off with 3, negative 3, 1, 1, negative 3, times xy is equal to, what's our eigenvalue? Our eigenvalue is negative 4 times xy. And so if you just take this and move it over to this side, it just effectively becomes a negative 4 right there and a negative 4 right there. And so check it out. This is going to be negative 3x plus y is equal to negative 4x. That's what the top line is going to be. And if you add 4x to both sides, you're going to get x plus y, which is what we ended up right there. See that? X. Let's see. That was going to be negative 3x plus y is equal to a negative 4x. And so if I bring this over, it's going to become x plus y. Yeah, that's what we have right here. It's going to become x plus y is equal to 0. And the same thing for the bottom. So it's easier just to do it all in one step and just subtract the lambda right from the start. Okay, so so then what? Then if you do things right, one of these is just a multiple of the other, so you can just get rid of one of them and you end up with x, multiply this out, x plus y is equal, let's see, x plus y is equal to 0, right there. X, this is x, 1x plus 1y is equal to 0. So there you have it. You let x be a scalar, t, and a parameter, and then y would have to be negative t, and so now you have, for negative 4, you let x be t and y be negative t, so you can have t times the vector 1, negative 1. So I just like to write the vector, eigenvector right there next to it. So there you have the eigenvalue and the associated eigenvector. Same thing here. You let lambda be negative 2, and you subtract negative 2's, which means you're adding a 2, and you do that all the way through, and you're going to end up with negative 1x plus y is equal to 0. And so you do the same thing as before. You let x be equal to t, then y is also going to be t. And so you notice that for this eigenvalue, you just end up with t times the eigenvector 1, 1. So there's your eigenvector right there. So once you have that, you have the general solution, which is going to be just any constant times this eigenvector times e to the negative 2t. And then beta times this eigenvector times e to the negative 4t. And again, if you want to, you could break it up and you could write x of t is equal to alpha e to the negative 2t plus beta e to the negative 4t. And then you could say y of t is equal to alpha e to the negative 2t minus beta e to the negative 4t. So you can write it either like this or like this, whichever way you prefer. So then, suppose, just to, again, to remind you what we did in the last section, suppose we're told that the initial value is 5, 3. So then you can stick in a 0 there, and you determine, I'm not going to go through all this. This is what's going to take too much time if I review all this stuff again. But you're going to find out that alpha is equal to 4 and beta is equal to 1. Notice that does it right there. Then you start with a 5 there, and you end up with a 3 for your y value. So that's just by way of a review. And now, what do the solutions look like? So here's what you do. So we're starting at the 0.53. Okay, there's the 0.53 right there. But instead of going along the axes, the way we do it instead is you think of going along these axes. Here's the eigenspace 1, 1 that looks like that. Okay, I like to write it like this. X is 1 and y is 1. So x goes in 1 unit and y goes in 1 unit. So there's the eigenspace associated with this eigenvector. That's negative 2. And then here's the eigenspace, 1, negative 1. 1, negative 1 down here is the eigenspace associated with negative 4. Lambda equals negative 4. 1, negative 1. Okay? So instead of going 5, 3, what you can think of it is, you can think of it as going 4 along this one, 1, 2, 3, 4 units, and then I think it's -1, isn't it? Let me see. No, just 1. Oh, 1 along this one. Yes, yes, yes. So you go 4 along this one, and then you go 1 along this one. So what's 1 going to be? 1 times this vector right there is going to be 1 unit in the x direction, and then -1 in the y direction. So you're going to end up right there is the point. You're going to end up at 5, 3 by the time you're done, once you do all that correctly. Okay, so the point is you move parallel to this one, and then you move parallel to this one, and so it's 4 of these plus one of these. This is the vector 1 minus 1. See that? There's the vector right there. 1 minus 1. So 4, 1, 2, 3, 4, and then 1 vector there, and you end up at 5, 3. So there's where you end up. So what does the whole solution look like? What happens to this thing as time goes on? So here is the key idea now. Notice that as time goes on, both of these things are getting small. You're taking e to large negative numbers, so they're both going to 0. However, and this is what's crucial, this one is going to 0 faster because you have a 4 in front versus just a 2 in front. So as time goes on, this one is going to go to 0, leaving this one left. So that one is going to be left. And so I'm letting t go to infinity now. This one is going to become insignificant. This part here is going to become insignificant. That's this vector, and this part's going to be left. So it's going to be something like this. It's going to come in along this eigenvector right there. It's going to come in along that. Okay, that's going to be true no matter where you are. If you start right here, it's going to come in along that one as well. If you start right here, it's going to come in along this one right there. Okay? If you start right here, let's see, I keep losing my, right here, it's going to come in along that one. So this is always the one that's going to be left, whereas the other one gets sucked down to 0, and you're going to come in along this eigenvector. On the other hand, what happens if we started at these points and you let t go to minus infinity? So you go in the other direction of the trajectory. So as t goes to minus infinity, now you have a negative times a negative. This is going to be a big positive number. That's going to be a big positive number, but which one is bigger? Obviously, this one is bigger, so as t becomes a large negative number, this one is going to dominate. So as t becomes a large negative number, then the trajectory is going to go off more parallel to this. It doesn't mean it soaks right up next to it, but it becomes parallel to it. And this becomes parallel to it, kind of like that. So this is going to become parallel to that. Same thing here, that's going to become parallel, and so will this one. Let's see. Oh, yeah. So will this one. Okay, so it's going to look something like that. So those are your trajectories. As t goes to 0, as t goes to infinity, they're all moving in this way. And so you put little arrows on there to indicate what's the direction. So they're flowing in like this. This is called, first of all, it's called a node. A node is by the way, this is a fixed point because right there at 0, 0, notice that at 0, 0, the derivative x prime is going to be 0 and y prime is going to be 0, which means there's no movement. So if you start off at that point, you're not moving at all. At all these points, you're moving in this way. If you start right there, you just stay there. So that's called a fixed point. This particular kind of fixed point is called a node. That's just the name of it, and it's called an attracting node because everything is getting sucked into it. Can you kind of see that if this would have been, I'm going to erase this now, so I'm just going to play with it now before I erase it. If these would have been positive eigenvalues, then these would have all been positive. And now as t goes to infinity, the arrows would roughly have been going like this. And I'm not gonna do anything more than think about it any more than just the arrows are going to be going in this direction now. If it's and that's called a repelling node. Okay, so that would be a repelling node. But I'm not going to say anything more about it than that. Okay, let you think about it from there. Okay, so I've got another problem for you to do similar to this one, and so there's that. Okay, so this is all one big problem here. Let's get on to the next one. Here's the next one. This is 851. This is problem 851 right here in the current edition of the book. It always keeps changing. And I'm just going to write it one way here now, just for brevity. 2, -4, 1, -3 times x. And I'm not going to go through all the eigenvalues and eigenvectors each time, because I'm assuming you know how to do that. In this case, here's the general answer. The general answer solution is going to be like this. So as soon as I give you the general solution, you know what the eigenvalues are. The eigenvalues are 1 and -2, and you know what the eigenvectors are associated with those eigenvalues, namely this and this. Okay, so if you want to check that out on your own, you can do it. But anyway, what we are doing now is we want to know, what is this thing going to look like? So let's do the same sort of thing we did before. We're first going to sketch in the eigenvectors. Okay, so one eigenvector is 1, 1, so that looks like this. Okay, so there's 1, 1, and that's associated with -2. I'm just going to put a -2 there. And then the other one is 4, 1, which means I go 4 units in the x direction and 1 in the y direction. So it's going to look like this. Okay? And again, notice that no matter what point you start at is going to be a combination of these two eigenvectors. So if I want to start right there, you could maybe, what would it be? Maybe it's moving this far along this eigenvector, and then you have to move this far in this direction. So you move this far along one, and then you move this far along the other one, which is parallel to that, and you're going to end up right there. So it's going to be some value of alpha plus some value of beta is going to get you there. Okay? By the way, you should realize that if you're right on in these eigenspaces here, that's where, like, for example, beta would be 0. If you start off right here, right? If you start off right there, then that means that you are just some number times this, gets you right there, means that this is equal to 0, and now you're going to be, well, what are you going to be doing? As t goes to infinity, you're going to be going straight out, right? You're going to be going straight out. And that makes sense because this is the eigenspace. What's true in an eigenspace? The movement or the direction is parallel to the vector. That's the whole point of an eigenvector, right? The derivative is the direction of it, the velocity of it is parallel to the position of it. Okay, so whatever the position is, the movement is in that same direction. Maybe positive, maybe negative, but it's in the same direction. Okay, versus being here, where here's your direction, but then the movement is something else. It's a combination of these two. Okay, so anyway, let's see once what happens. Let's just start right here and see once what happens. Okay. So this one right here, let me put it right here just so I see it in front of me. This is 4, 1, and this is eigenvalue of 1. Okay, so what's going to happen to this one now? As t goes to infinity, as t becomes a positive number, this is the one that's going to dominate. This one is going to go to 0. So this portion right here, the portion that's in the direction of this right here, is going to get smaller and smaller, and I'm just going to get closer and closer to this thing. So it's really going to become kind of an asymptote, because this is really going to be the entire. This is going to be the entire. Think of what happens as t gets large. It's going to all be this stuff. This is going to be basically minimal, and so you basically have, it's going to be all this stuff. So it's going to look like that. So it's going to look like that as t goes there. Down here, same thing. It's going to go like that. Right here, it's going to go like this, and it's going to go like that again. That's going to be your vector. Oops, let me make sure that you're all still there. Hopefully you are. Yep, very good. Okay. Notice, by the way, that we don't. Well, yeah. Okay. Be careful here. So anyway, so that's what happens. What happens as t goes to negative infinity? As t goes to a negative infinity, then negative times a negative is going to be positive. This is going to be your large contribution, and this one's going to go to 0. So now it's going to go along the vector 1, 1. So it's going to look something kind of like this. And this one's kind of going to go like this. And this one's going to go kind of like this, get closer and closer to here. And this one's going to go, let's see, where are we? Right here. Like that. Okay. So better pictures in the book, but that's the general idea. Okay, so see what's happening? It's shooting out here, shooting out there, kind of coming like this, coming like this. This is called a saddle point. Saddle point. Why is it called a saddle point? If you think of a saddle, if you think of it in one direction, it looks like this, but in the other direction, it looks like this. So kind of depending on where you are in the saddle, either it's going up or it's going down. And so this thing here, either it's coming in from one side and going out on the other. Okay, so that's that one. Okay, very good. Next one, and I forgot to put down the numbers for these things, so I'm not going to try to find them now. Okay, but the next example I want to do from the book is this one right here. And there's lots of discussion here. So again, I'm not going to go through everything because I'll lose you the forest for the trees. But what I do want to do is I want to find the eigenvalues. So it's going to be minus lambda, 1, negative 4, minus lambda. And you're going to end up with lambda plus 4 equals 0. And so, of course, you get lambda is equal to plus or minus 2i. Okay? What do you do when you get imaginary numbers like that? And so a lot of stuff in the book, but I'm going to give you just the final result. And here's the final result. That your general solution is going to look like this. If you have pure imaginary, there's no real part there at all. It's just going to end up being, let me get it here. It is alpha times cosine of 2t, negative 2 sine of 2t, plus beta times negative 2 sine of 2t, and then negative 4 cosine of 2t. Okay, basically, what you do is, you see this 2 right there, this becomes a cosine of 2t, that number right there. This becomes its derivative right here, which is negative 2 sine of 2t. See that? So the derivative of this is right here, negative 2 sine of 2t. And then same thing right here. This is the derivative of this. And notice that this is the derivative of this. Okay? So that's the relationship between all these things. So these two things are two linearly independent vectors. Notice that one is not a multiple of the other, so they are linearly independent, and that's what we're looking for, is two linearly independent vectors. And we want to show, let's go ahead and just show that indeed they are both solutions. Let's just take this one right here and show that it's a solution. What do we have to do to show it's a solution? This thing says right here says to do what? We take the derivative of it. So if we take the derivative of it, what do we get if we take the derivative of this thing? It's going to be what? It's going to be negative 2 sine of 2t, and you take that's what we're doing with it. We're taking the derivative of this thing right here, and it's going to be negative 4 cosine of 2t. Agreed? That's the derivative of this. Okay, and now what does this side say to do? It says to take this vector right here and multiply it by this matrix. And hopefully we'll end up with the same thing. Let's check it out. Here we're going to get a negative 2 sine of 2t. This times this and this times this, and then here we're going to get a negative 4 cosine of 2t, and then 0 there. So sure enough, notice that when we take the derivative, this is the derivative right here, and this is multiplied by the matrix right there, and sure enough, they are equal. And that would also hold true for this. So they are two solutions of this. They are linearly independent, and so that's all we need. Okay? So once you have those, then what does that solution look like? So let's go ahead and write it out. Let's write x is equal to alpha cosine of 2t plus, or say minus 2 beta sine of 2t, and here's y is equal to what? Negative 2 alpha sine of 2t, and then here it's going to be minus 4 beta cosine of 2t. And this is again something that we've done before. But if you take x and y and you square x, and then you take y and divide it by 2 and square that, so just square x and square y over 2, you're going to end up with, I believe it's alpha squared plus beta squared, a constant, depending on what alpha and beta are. And that's the graph of an ellipse. It's a graph of an ellipse where the y value is twice as high as the x value. Looks something like that, and the size of it depends on alpha and beta, but it's going to be some sort of an ellipse. Okay, so those, depending on what alpha and beta are, those are your different solutions. They're just going to be different solutions that look like this. Those are your trajectories, and then the only question you really have to ask is, what direction are you going along those things? Are you going clockwise, or are you going counterclockwise? And the way to check it out is just to, let me see, I just thought about this a minute ago. Let's see, what do we have here? Let me write it out. We have x prime is equal to, what does this say? X prime is equal to 0x plus y, and y prime is equal to, y prime over here is going to be 4x, just 4x plus 0y, okay? I guess there's no reason to have those there. Okay, so you have this, and you have that. That's what it's saying to do. So notice that if you're at a place right here where x is equal to 0, okay, very good, I'm still working here. This should be negative 4. Negative 4x. Okay, so where x is equal to 0, then notice that what's happening? I'm sorry. Y is equal to 0. Y is equal to 0, and x is positive right there, right? This is the x-axis. There's your y-axis. So y is equal to 0. Since y is equal to 0, that means that there's no movement in the x direction right at this point. Sure enough, if you're on this trajectory, you're not moving at that particular point. You are not moving in the x direction. As soon as you get over here you are, but right there, you're tangent to, you're not moving. On the other hand, what's happening in the y direction? If x is positive, notice that that y is going to be, the derivative of y is negative, which means y has to be decreasing. So when x is positive, see that? X is positive, y has to be decreasing, which means you have to go like that. So that tells you that we're going in the clockwise direction, and you can use that at any of these points, and everything will confirm. You're going to keep going like that. Let's just do this one right here, just as another example. If y is negative, what does that tell me? It tells me that x is going to be going in the negative direction. Sure enough, x is going in the negative direction. And so sure enough, we're going like that. Okay? So that's that one right there. Now, what happens if instead of having a lambda here, which is just imaginary, what happens if it's complex? What happens if we have a real part as well? So let's do an example like that as our next one. Okay, and just to give you some motivation for this one, let's take our example from an earlier chapter where we had the mass problem. This is where you have a mass of mass 1, and the friction constant is 1, and the spring constant is 1, just to keep things easy. Okay, so you've got a mass on a spring, and there's some friction, and you take it back to the original position, and what's going to happen to that spring? If you have that mass, hopefully, what's going to happen? Since there's friction, it should do something like this, right? It should eventually come to a standstill. Okay, it should come, or at least the vibrations become smaller and smaller. Let's see what happens if we solve this thing with a system of differential equations. Here's how we're going to do it. This is something I did in an earlier section. I'm going to do it again. I'm going to let y, notice that this is a function of a differential equation of second order with just one function. I'm going to change it into a system of first order differential equations. And the way you do it is you let y be equal to x prime, okay? And then y prime, of course, is going to be x double prime. But x double prime is just equal to, if you bring this over, is going to be equal to negative x and then negative x prime. But negative x prime is just going to be negative y. See that? So here you have it. So here, let's write it again. X prime is equal to 1, is equal to y, and y prime is equal to negative x minus y. So if you write that as the system, what does that become? It's going to become, let me do it, let's see, 0, 1, negative 1, negative 1. Okay, check it out. X prime is equal to y. Y prime is equal to negative x, negative y. There you go. Okay, so there you have it. Now, again, I'm not going to go through all the work here, but if you find your eigenvalues are going to be negative 1/2 plus or minus the square root of 3 over 2 times I. There's your imaginary part. There's your real part. And so once you have that, here's your solution. It's similar to what we had before. It's just that you have to have this real part as well. It's going to be alpha. Here's the real part, e to the negative 1/2 t. And then this imaginary part, you do the same thing as before. You start with a cosine of this thing. And then you take its derivative right here. It's going to be negative square root of 3 over 2 sine of square root of 3 over 2t right there. And then you take its derivative, and then you have your beta, e to the negative 1/2 t. And then the same thing over here. You take the derivative of this, and you're going to get negative square root of 3 over 2 sine of that t. And then its derivative down below. And if you take its derivative, this comes out, you're going to get negative 3/4 cosine, if I'm doing it right. And there you go. So, so what does this solution look like? This thing right here, if you wanted to, you could basically factor this part off, and then you've got the same solution that you had before. So that same solution you had before is going to give you this oval, this ellipse. But now, as you go around that ellipse, what's happening? Everything is being multiplied by this thing, which as t goes to infinity, this thing is going to be getting smaller and smaller and smaller. So instead of being an ellipse that comes back to itself, it's going to be an ellipse, which as it goes around, it keeps getting smaller and smaller and smaller, like that. And that's exactly, think again, realize what's happening. This is your x, this is your y, and remember that y is equal to your velocity. So this, you've got this mass, and this mass starts right here, and every time it makes a kind of a period, it comes back. It doesn't come as far again. It doesn't come as far. It doesn't come as far. So not everything is slowing down. See, the velocities are getting smaller. They're not as large as they used to be, and the distances that it goes. So the spring is it's going slower and slower and slower and slower, and it never actually hit 0 there, but that 0 again is the fixed point. By the way, this is called a center when you have a circle. I told you the saddle point and the node, and this is called a center. You know what? I'm not even sure if this is called a center or not. I don't think so. Maybe a spiral center. I guess I can't remember if that has a name to it or not. But anyway, that's that one. Okay. So what's left? We're kind of the ones we've just done are probably the most important ones, but there's still some interesting ones left, and you should. I kind of want to, as a good teacher, I want to give you a good comprehensive course and give you all the material. So here is an example where you have double eigenvalues. And this gets more into linear algebra again, but if you have something like this, then basically all you're saying is that x prime is equal to 3x and y prime is equal to 3y, and we can solve those from things we did back in the first chapter. This is going to be x is equal to alpha e to the 3t, and this is going to be y is equal to, say, beta e to the 3t. And so you just end up with, you know what, I'm not going to go through this much anymore. Basically, here's what you end up with. Everything is moving just in the direction of the, how should I say? Everything is an eigenvector, okay? Because every single vector you put in here, the derivative is just going to be 3 times the vector. So if you're right here, the derivative is going to be 3 times as great. If you start right here, the derivative, that is the velocity, is going to be 3 times as great. So no matter where you are, you're just going to keep going in that direction. So it's called a star. It just radiates out from the center. Okay, so that's another kind of behavior, and that's called a repelling star. And you can probably guess that if you had negatives there instead, then these arrows would be coming this way, and so that would be an attracting star. Okay, good choice of words all the way around. Okay, so every single vector, and I'm not going to go through all the details of that one, but that's another important one. Okay, here's one that's a little more ambitious. Suppose you have this one. You have okay? If you go through this one, you will find that the eigenvalue is 3 and 3. It has a double eigenvalue of 3, but you only get, unlike the past problem that basically had eigenvectors that look like this and another eigenvector that looked like this. So you had lambda equal 3 and lambda equal 3, so you had a double eigenvalue called an eigenvalue with multiplicity 2, but we had 2 different eigenvectors as well, which basically said everything in the plane was an eigenvector in this case. In this case right here, you have a double eigenvalue, multiplicity 2, but the eigenvectors are just of dimension 1. Basically, you just have 1, and that one is this one right there. Okay, so you go through, let me make sure that you're all with me again. This is a long lesson. Very good, okay? So there's your eigenvector. So question is, we've got a double eigenvalue, but we only have one eigenvector, but we know this is a system of two first order differential equations, linear, so we know that there's got to be another one. So what do? And so we do the same thing that we've done 2 or 3 times previous in the book. Remember how we do it? We kind of find this way to get this other one by throwing in a t. We throw in the variable, the variable, and we're going to do something very similar here. Okay, here's the method. Here's what you do. So what you do is this is called a generalized eigenvector. Generalized eigenvector. And the eigenvector we're going to call z, which is z1, z2. And what we do is we take this thing and we subtract the eigenvalues down the main diagonal. So it's going to be 2 minus 3. I'll go ahead and write it that way. 2 minus 3, 1, negative 1, 4 minus 3. Okay, and then we multiply that by the generalized eigenvector z1, z2, and we set that not equal to 0, but we set it equal to this eigenvector. And so we're basically getting another one, kind of similar in spirit to the way we did it with second order DEs. Okay, kind of similar in spirit. And so anyway, what happens? We get the same sort of thing as before, where these 2 equations are both saying the same thing. Notice this, negative 1, 1, negative 1, 1. They're both the same. So all I have to do is write one of them down. Negative z1 plus z, oops, this should be a z2 there, plus z2 is equal to 1. And then you do the same sort of thing as before. You set one of those equal to a parameter. So I'm going to set z1 equal to t. And so z2 becomes 1 plus t. See that? And so this then, I'm going to break it up and write it as the vectors 0, 1. That's the scalar part, or just the part without a t in it, and then t times 1, 1. See that? So I can write this, I can write it like that. And so this is my generalized eigenvector right there. And so here is the final result. The final result is that it's going to be alpha times my first one that I found legitimately. And by the way, these both have to have a e to the 3t on them now. E to the 3t times 1, 1. Okay. And then plus beta e to the 3t times this generalized eigenvector. 0, 1 plus t 1, 1. Okay, so there's your general solution. And again, I'm not going to go through all the details here, but this thing is kind of what happens. Let me just say it this way. It's kind of like your node that we had at the beginning. But the nodes that we had at the beginning, we had, two different eigenvectors. We had one like this, and we had one like say this, and then it came in along one and went out along the other. But now these are being squeezed down into just one. So instead of having two of them, we have just one of them. And so what happens is that this thing kind of serves both purposes. If you go out really far, it goes parallel to it. But when you come in, it also comes in parallel to it. So it's kind of like instead of having two parents, one parent does one thing, one does the other, you have one parent that does both things. Okay, that's the analogy that comes to mind. Okay, so it serves both purposes. Okay, it serves both purposes. So it looks kind of like that. So those are your solutions. Okay, now the last thing I want to do with this is just to show you that this seemed kind of strange. I want to prove to you that this indeed is a solution to this. Okay, so how do I show you that that's a solution? Let me erase this stuff. And let's this is for sure. You can show this one as well, but this is the more interesting one. So let me show you that this thing satisfies this differential equation. What does this say to do to it? This says to take the derivative of it. Okay? So let's first take the derivative of this thing. If I take the derivative of it, let's just say x. Let's just gonna let my x be equal to 0, 1. E to the 3t times 0, 1 plus t times 1, 1. Okay, there's my x. So if that's my x, then what's x prime? What's the derivative? Well, let's see. Let's do them one at a time. What's the derivative of this thing? This is going to be 0. The derivative of this is going to be 1 times this is just e to the 3t. Its derivative is going to be 3 e to the 3t. Agreed? Okay, what about this portion? Oops, I need my e to the 3t on the outside of this. E to the 3t is times the whole thing. So I've got e to the 3t times this thing. Let's just call this t and t here. T and t. T times 1 is t. So, what's that going to look like? What's the derivative of t e to the 3t? Well, let's see. What's its derivative? We're going to have to use the product rule, right? The product rule says you take the derivative of the first times the second plus the first times the derivative of the second. Derivative of the second is 3 e to the 3t. So the derivative of this thing is going to be e to the 3t plus 3t e to the 3t. And same thing down below. E to the 3t plus 3t e to the 3t. Agreed? So if you add all that stuff together, first of all, let's factor the e to the 3t out, because everything has an e to the 3t on it. Here I end up with 1 plus 3t up on top. And here on the bottom, notice I'm going to have 3 of these, plus one of them is going to be 4 of them. And I'm going to have, I factored this out again, so I'm going to have a 3t here. Okay? So there's what happens when I take this thing and do this to it. Now, let's do this to it. What does that say to do? It says to take 2, 1, negative 1, 4. And what do I want to do? I want to take that thing and apply that to, let's see, I can apply it to, first of all, this constant can come out front. So I'm just going to write it as e to the 3t, because everything's going to have that. And so I'm going to apply it to 0, 1. And then I'm going to break it up into 2 pieces. And I'm also going to apply it to the TT. And what do we get when we're done? We're going to get e to the 3t. Now what did I do? I applied this thing to both parts of it. When I apply it to this, what do I get? I'm going to get 0, 1. And here I'm going to get 0, 4. Okay. And then what happens when I take this times this? I'm going to get 2t plus 1t is 3t. And here I'm going to get negative t plus 4t is 3t. So notice here, I get e to the 3t times, if I add these together, I'm going to get 1 plus 3t. And add these together, I'm going to get 4 plus 3t. So pretty cool. That's to verify, and I asked you to do this in your problem as well, to verify that sure enough this thing is a solution to this. So we proved its solution. We stuck it into, we plugged it in, and when you do both things to it, you get exactly the same answer. Okay, I'm glad that worked out. Okay, very good. The last one more I want to do. And this is an important one for some of our applications coming up. So what's interesting about this one is what happens when you have eigenvalues of 0. How does that, what happens with those? So there's just all sorts of interesting things here that come from this. Okay, if you go through the same process again, I'm just going to give it to you. You're going to end up with lambda is equal to 0 and I have 7, but I think it's negative 7. Let's go ahead and do it real quick. So let's go ahead and do it. So it's going to be negative 1 minus lambda, 3, 2, negative 6 minus lambda. Agreed? We want the determinant of that. And so notice all these negatives. So I'm going to multiply these. The negative times the negative is positive. So it's going to be lambda plus 1 times lambda plus 6, all minus 6. Minus 6, agreed? So that's equal to lambda squared plus 7 lambda plus 7 lambda plus 6, and then minus 6, so those go away. And I get this is, of course, equal to lambda times lambda plus 7 is equal to 0. So sure enough, I think my memory was right. The two eigenvalues are lambda is equal to 0 and negative 7. Okay, those are your two eigenvalues. Okay, negative 7. And if you find the eigenvectors for each of those, should we do one more just for practice? Let's go ahead and do the one for negative 7 just for practice. So I like to kind of go like this, put it off to the side here. So I subtract the negative 7. If I subtract the negative 7, that means I'm adding 7, which means it's going to be 6, 3, 2, and now I'm adding 7. So it's going to be 1. See that? Again, notice if you have 6x plus 3y is equal to 0, that's just a multiple of 2x plus 1y is equal to 0. So I always just get rid of the bigger one and write it as, I shouldn't have gotten rid of that, and I'm going to end up with 2x plus y is equal to 0. Let x be equal to t, so y is equal to negative 2t, and so now I know that there's my eigenvalue. I like to put these in brackets like this. It's going to be what? T times 1, negative 2. So there's my eigenvector for that one. The eigenvector for 0 is 3, 1. Okay? So what happens here? This is kind of interesting. As I say, this is going to come up in some applications here. So what do these two eigenspaces look like? 3, 1. That means okay. My computer went almost until the very end of my talk here, and then it froze. But that's okay. All I did was I'm talking about making the eigenspaces for each of these eigenvalues. So 3, 1, you go 3 over and 1 up. So there's the eigenspace associated with the eigenvalue of negative 7. And then what's the one for the eigenvalue 0? It's 3, no, I'm sorry, 3, 1. This is for 0. Sorry, that's for 0. And then negative 7, that has the eigenspace of 1, negative 2, which means I go 1 over, negative 2, 2 down. Or I could go 1 over and 2 up. Point is, one of them is positive, one of them is negative. So there's your eigenspace right there. And that's the eigenspace associated with 1, negative 2 with the eigenvalue of negative 7. So, first of all, what does your solution look like? Here's your general solution. Your general solution is going to be what? Alpha e to the 0, of course e to the 0 is just 1, times 3, 1, and then beta e to the negative 7t times 1, negative 2. So what's going to happen? Let's just think about it. You start off at some point here. This point is going to determine your alpha and your beta. Okay, you're going to get some alpha and some beta depending on what point you're at. And then what happens as time goes to infinity? As time grows, the 3, 1, this portion, you can kind of think of it like this. It's this vector. These are almost perpendicular to each other, not quite, and then this vector. Okay, so as time goes on, this portion right here is going to stay put. This is the one that's going to attenuate to 0. It's just good. This portion of it is going to just go to 0, and so this is just going to come. It's going to be parallel to this vector, and it's going to just come on in like that. No matter where you are, it's going to be this portion of it, which is just going to go to 0, just leaving you right there. So the point is you've got a whole eigenspace of fixed points. Anywhere along here, instead of having just one fixed point at the center, you got a whole row of them right there, or I should say a whole line of them, there, which is your eigenspace. All those are fixed points. If you start off right here, that's going to be that beta is going to be 0, and you're just going to have that, and you're just going to stay there forever. You're not going to change at all. Okay, so there you go. So that's the last one. So there you go. This was a very good, long, comprehensive lecture. So hopefully, along with the book, you got what you need to do the different problems here. Very good. Oh, by the way, just a quick, the next thing we're going to do is, in the next section, we're going to show a very clever way of kind of seeing what the behavior is just by looking at these numbers. Just by looking at these numbers right here, we can see exactly what kind of behavior you're going to get rather than go through this whole process. So that's what's coming up.